Hi everybody. In this section we're going to look at optimization, which is applications of local minimum and maximum problems, critical points, and absolute maximum and minimum problems. So it's just a bunch of applications of that stuff. So the idea here is that there's lots of practical applications. So this is all applications. So we might want to look at a business person minimizing costs and maximizing profits, and maybe there's a constraint. So the price of the item, like the sales might change based on the price of the item, so you have to sort of like take into consideration how sales change. A traveler wants to minimize transportation time. Maybe there's some other constraints there, like the cost of gasoline or something like that. And then the third one is a physics one. Fermat's principle in optics states the light follows the path that takes the least time. So there'd be physics constraints there, like the physical reality of the object. So in this section, we solve problems such as maximizing areas, volumes, and profits, and minimizing distances, times, and costs. So it's a big mix of problems on your homework. You will have a activity sheet that has some homework problems and a mix of problems I'm doing here and a mix of things you might see on an exam. So make sure you get a chance to do that activity sheet, even though I'm not collecting it. So in general, we just want to do some general problem solving techniques. You want to make sure that before you write anything down, so these problems are similar to related rates, but they're much tougher. So you always want to make sure you understand the problem. You want to know what's given, what's unknown, and then what's the constraint, right? So because there's usually multiple variables in the problem, at least to start, you have to get the problem down to one variable to take a derivative. So the constraint is a way to turn one variable into another. Draw a picture if you need to. Then assign values to symbols. Use letters that make it easy to remember what each represents. So if you're doing an area problem, use A. If you're doing a profit problem or a price problem, use P. And then next one, express the unknown quantity in terms of the symbols of the known quantities. So you want to make your unknown quantity a function of known quantities. Then combine and simplify equations so the unknown quantity is expressed as a function of a single known quantity. So you just want to reduce it. And once you have Q equals f of x or A equals f of x or whatever it is, then you can take a derivative, find the critical values, find local maximum and minimum or global maximum and minimum. And that's what we're going to be doing. So let's jump right in here and do the first one. So we have a piece of wire 7 meters long is cut into two pieces. One piece is bent into a square and the other is bent into an equilateral triangle. How should the wire be cut so the total area enclosed is a maximum or a minimum? So you might look at this and go, well, this doesn't make any sense. How is this an application problem? Who would do this in the real world? Well, it turns out that people who design like gardens have to enclose things in either bricks or fencing. And this kind of stuff actually comes up all the time. So let's think about it, right? You have a square and a triangle. You have one piece of wire. You have to cut it, bend one piece into a square, bend the other piece into an equilateral triangle. So first, let's look at the square. Let me get myself out of here a little bit. So let's look at the square first here. So we're looking for x, right? So let's go back here and look at the problem again. Look carefully how the problem's stated. How should the wire be cut so the total area enclosed is a maximum, right? So the way that the wire is going to be cut, I'm just going to use x as here's the amount of wire that we're dedicating towards the square. Everything else will be the triangle. So I'm just saying this whole distance around is x. So there's 4 sides, so the length of one side is x over 4. So the area of the square is x squared over 16. Great. Now let's look at the triangle. Triangles are a lot tougher than squares. So I'm calling the perimeter here y. And so because there's 3 equal sides, then the base is y over 3. And this side here is y over 3. So the area of the triangle is just going to be 1/2 y over 3 times h, right? It's 1/2 base times height, but the base is y over 3. Now this is an equilateral triangle. Each angle is 60 degrees. So I'm just going to use trig properties to find h here. So h is y over 3 times sine of 60 degrees, right? Or pi over 3. So this is this is r. If you put this thing inside a circle, this is the length, this is the radius of the circle. And so I'm just using the definition of sine on the unit circle. So it's just y over 3. Sine of 60 is radical 3 over 2. So I get y radical 3 over 6. So that's the height. Plug this into my area of the triangle. So it's 1/2 base times height. You get y squared radical 3 over 36. So we have the area of the square as a function of x, the area of the triangle as a function of y. And we want to minimize the total area. So we add the areas of the square and the triangle. We want to minimize that. We want to do this as a function of x or a function of y. And the constraint is that the total perimeter, x and y together, sums to 7 meters. Right, the perimeter of the square plus the perimeter of the triangle is 7. So we need to get the function to be optimized, which in this case is the area, in terms of a single variable. It doesn't matter if you pick x or y, you're going to get the same answer. So I just know x plus y equals 7. I solved this for y. So anytime I see a y in my equation, I'm just going to plug in 7 minus x. So I put this into the triangle equation, and then I write it out. So this is here's your square. This is this right here. Here's your triangle. And then wherever I saw y, I just plugged in 7 minus x. So this is my function, but I don't want to take a derivative off of this. Remember, derivatives don't like things to be factored because then you have to use the chain rule. We'd rather not use the chain rule, right? So what I did is I FOILed this right side, right? I just FOILed this out, so it's radical 3 over 36, and then just FOIL this out. Now I don't have to use a chain rule because my constants are all out front, right? So this is going to be much easier. So I can go ahead, take a derivative to find the critical values. So the derivative of this is x over 8. This is a constant, so it stays a constant. And then I just take the derivative of this. So it's negative 14 plus 2x. Set this equal to 0. So first round of algebra, I distributed these two values, and then I just rearranged. So I factored out the x, so it's 1/8 x. Here we have radical 3 times 2x over 36. So the 2 and the 36 cancel, 2 and 18. Radical 3 over 18, and then here's the x. And then here we have negative 14 times this. So it's just negative 14 radical 3 over 36, which is negative 7 radical 3 over 18. Next, I moved this to the other side, and I multiplied through by 72 to get rid of the denominators. It works. You can try it. Next, I just solve for x. So x is 28 radical 3 over 9 plus 4 radical 3. So this is the exact answer. So if this turns out to be a local minimum, then this is the answer you have to type into WebAssign. However, I need to do a sign diagram or a second derivative test or something to find out if this actually is a minimum. So when I plug numbers in to test, I just rounded it to 2 decimal places just to run the test. You can't type that in as an answer on the homework. It's going to make you type this in. So we want to optimize A. So notice we have the area is a function of x up here, right? It's at the top. This is only a function of x, but it's on a closed interval, right? The smallest amount of wire you can dedicate to the square is 0, and the most wire you can dedicate to the square is 7. Remember, x is how much wire we're dedicating to the square. So there are physical constraints here. So we need to check, if the critical value or the endpoints are local min or local max values. So what we do is we plug the critical value and the endpoints into our area equation to find out if we have a maximum or minimum. So here's what we get. So when you plug everything in, and again, I just rounded everything. If this were a homework problem and you had to turn in the y values or the a values, they'd have to be exact values. This one's not too bad. If you plug in x equals 0, you just get 49 radical 3 over 36. But again, I'm trying to compare what's a maximum, what's a minimum. So having a bunch of radicals doesn't help. I want to see the decimals. That's clearly a minimum, and that's clearly the maximum. So the total area is a minimum when x equals, for the homework, you got to type in that horrible, ugly thing, but you have to do it. And then it's a maximum when x equals 7 meters dedicated. So when you split this wire between a square and a triangle, you get the biggest area when you give it all to the square and you make the triangle size 0. So there you go. Not a bad problem. It's a lot of arithmetic. There's really not that much algebra. It's a lot of geometry and a lot of arithmetic. Every problem that you're going to see in this section is different. So I'm going to go through a few of them, and you'll see how it works. But there's a lot of techniques that you guys have to figure out on your own. Next one up. This is another sort of graphing type problem, but it's not geometry per se. It's more algebra. Find the point on the line 5x plus 3 that is closest to the origin. So think about it, right? You have a line in space somewhere, and one of the points on the line is the closest to 0, 0. So I just drew a little graph, and I kind of estimated where I thought it was going to be, but I don't know where it is, so I just called it xy. So given a pxy, we wish to minimize the distance between P and O, subject to the constraint that P is on the line. So again, we need a constraint here because this thing has 2 coordinates, and in order to take a derivative, you can only take a derivative with 1 coordinate. So we just use the distance formula, right? The distance between any 2 points, x1, y1, and x2, y2 is given by the distance formula. So we can just plug in the coordinates here. We can just plug in x, y, and 0, 0 down here. And it simplifies to that, which is pretty nice. But again, I still can't take a derivative, right? I want to minimize this, but there's still 2 variables here. So now I use the constraint. So P lies on y equals 5x plus 3. We substitute this into the formula. Then you do some algebra. And then you're ready to take a derivative. But before you do that, I want you to look at this function and say, is this really something I want to take a derivative of? In other words, is there another way to minimize the distance between the points without taking the derivative of this function? If you're not sure what to do, pause the video now and think about it. Because this is the kind of mental gymnastics you're going to have to do in a class like this. This class is not like algebra where we hold your hand through everything and spell everything out. You're going to have to do some creative solutions on tests, or you're going to have to take the derivative of that ugly thing and look at it. Right? That's got a chain rule and a power rule. Rather not deal with that in the middle of this big problem, right? So pause the video if you're not sure, and think about what you can do instead of taking the derivative of this. So it turns out we can minimize the square of the distance, and it would also minimize the distance. So that should make sense, right? If you have 2 squares, that's why it's called squaring. If you have 2 physical squares, and one has a smaller edge, it also has a smaller area. So if we're trying to minimize the size of something, we can minimize the square of the size. So what we're going to do is create a new function called z, and we're just going to make it d squared. Right, so here's my z function. So minimizing this will also minimize this. Okay, because that's how numbers work. This is not even an algebra property. This is like a property of like objects on a piece of paper. Well, I'd much rather take the derivative of this guy than this guy. right? So this is a nice, very simple technique that you're allowed to use, like the MPQ function in Chapter 1. The MPQ function is a lot easier than plugging those numbers into plugging it into the function every single time. The MPQ function makes the work easier. Well, squaring this thing makes the work easier. So we're going to take the derivative of z and set it equal to 0. So that's an easy derivative, easy to solve. So you get a critical value of negative 15/26. Now you'd get the same number if you took the derivative of d, but yucky yuck. Nobody wants to do that. Not even me, and I like this stuff. So is this guaranteed to be a minimum? It's not, because we're on an open interval here, and we only have one critical value. It's possible we could get a maximum. When you have a closed interval, you can always just compare the numbers to each other and pick the biggest and smallest number on the interval. But on an open interval with one number, you have to use the first derivative test or second derivative test. For most of these application problems, the second derivative test is easier because you've already taken the first derivative and you only have one critical point. Remember, to use the first derivative test, you'd have to make a sign diagram. I really don't want to do that, right? I'd much rather just take the second derivative and then decide, is it concave up or concave down? So if the second derivative is positive, that means the function is concave up. And that means that the critical value must be a minimum, and that's the second derivative test. And if it's a local minimum, it's an absolute minimum, right? Because it's concave up. This thing never switches direction and comes back down. It's a parabola. Look at it, right? Go back and look at the function, right? This is a positive parabola. It never goes back down. It just comes down once and goes back up. So then we plug this into the equation of the line. So now that we know that our x-coordinate is a minimum, we plug it into the equation of the line, and we get a y-coordinate. And so our answer then is the point on the line that is closest to the origin is negative 15/26, 3/26. And that should make sense, right? So if you go back and look at that diagram I drew a few slides ago, you'll see that my guess is awfully close to that value, right? Barely above the x-axis, right? And if you want to check your answer, just a quick way to check. The slope of the y-coordinates here, so if you go y divided by x, it's the negative reciprocal of this slope. So this divided by this should be negative 1/5, and it is. So just a quick way to check. Because it's hard to check your answer with stuff like this. All right. So again, I put this in the notes. If you guys don't like this squaring method, it'll work every time. But if you don't like it, anytime you have a distance, you can use this. Okay? You're going to get the same answer. You can use any method you want, but the derivative calculations are much easier using z. So just keep that in mind. It's going to be better for you in the long run, or maybe even the short run, to learn a new technique, because it makes these problems easier. None of these problems are easy, as you've already seen. All right, let's do one more. This time we're going to talk about some economics. We've seen some of this stuff before. I didn't really go over it in the videos, but you had one problem on the homework that kind of explained all this stuff, and it was a step-by-step problem. So this is just some review stuff from that, and we're going to see a new application. So if C of x is the cost of producing x items, the marginal cost is C prime. And this is just the cost to produce one additional item at that production level, right? So C prime of 50 means if you've made 50 cars or whatever, motorcycles, then the cost to produce the 51st one will be C prime of 50. Now, what about marketing? So P is the price per unit. So P is called the demand function or price function. Those of you who have taken some econ, you know about P of X and Q of X. So we're just using P as price function. Again, if you want to call it the demand function, but I know there's multiple demand functions. So we're just kind of doing the easy version for folks that don't know economics. Now, if you sell X units and the price per unit is P of X, then your revenue is the number of units sold times the cost per item, right? That's basic econ, lemonade stand level econ. So if you sell 10 cups of lemonade for $1 each, you made $10. If you sell 8 cups of lemonade at $2 each, you made 16. So you want to set the price to maximize revenue. But the price is a function of the number of items sold, sort of in the real world, right? So on the business side, they look at how many items are sold and set the prices accordingly. So price is a function of X if you're the business. If you're the consumer, you might think of X as a function of P. So we're looking at it from the business side here. Well, the derivative of this is called the marginal revenue, and it's the revenue per item. And if X units are sold, the total profit is just capital P, which is the revenue minus the cost. And of course, there's a marginal version of that. And so we're not going to go real deep into the economics here. Just a couple examples, show you how it works. So what we're going to look at here is how to optimize ticket prices to maximize revenue. So we're looking at it, again, from the point of view of the business. So a baseball team plays in a stadium that holds 55,000 spectators. With ticket prices at $10, the average attendance had been 16,000. When ticket prices were lowered to $8, the average attendance rose to 24,000. Find the demand function. Price P is a function of attendance X, assuming it to be linear. And then for part B, how should ticket prices be set to maximize revenue? So there's a lot going on here, but we'll start with part A, and then we're just going to plug everything in. So notice it says this is a linear function. So in order to find a linear function, you need to have the slope and a point or 2 points. Well, we're given 2 points here, right? So first find the slope of the line and then use point slope form. So that's what we're going to do. So we're given 2 points, right? We're given, so I just used y in place of p here because I wanted to keep x. You know, x is still the independent variable, right? Like y equals f of x. So here it's just y equals, p of x, basically. So we're given, so when the attendance is 16,000, that was when tickets were $10. When the attendance was 24,000, the tickets were $8, right? So we find the slope. It's just y2 minus y1 over x2 minus x1. Plug everything in, you get negative 1 over 4,000. Pretty easy stuff. Plug that into your point slope form. All right, just plug everything in. We know what all those values are. You've got them listed. And then simplify, right? So here's our demand function. And it should make sense, right? So here's your attendance. As attendance goes up, ticket prices go down because the more people come to the ballpark when tickets are cheaper. Remember, from the business perspective, cause and effect are reversed, okay? Now what do? Well, we want to maximize revenue on the interval 0 to 55,000. So let's make sure we understand why. X is the attendance. The minimum attendance possible is 0. The maximum attendance possible is 55,000. So we're on a closed interval. When you're on a closed interval, you don't have to use first or second derivative test unless you have lots of critical points. We're looking for absolute max, absolute min, right? Those have to occur at critical points or endpoints. So we plug in the revenue function. Right? We know P of X, so we just plug everything in. Right? We just carry that over from the previous slide. Now this is what we're trying to optimize. So we want to find the derivative and set it equal to 0. Very easy derivative. And you solve this and you get 28,000. So that's a critical value. So this is the value that either maximizes revenue or minimizes it. We don't know unless you want to do a first derivative test, second derivative test, or because it's only one critical value on a closed interval, we can just plug in the endpoints and compare everything. And that's what I did. So I typed in the 2 endpoints. I typed in the critical point. Oh, sorry, that's a little typo. That should be 28,000 there. I got it right over here. That's just a goof. That should be at 28,000. And you can see that the maximum revenue comes from when X is 28,000. That's no surprise, right? If nobody comes to the ballpark, it doesn't matter what the ticket prices are, right? And if so you can plug it back in the original equation and see what happens. If 55,000 people come, tickets are really, really cheap. But that means you don't make enough money for all those people that are there. So it's got to be a combination. You have to set the prices so that enough people come that you make some profit. We're not even getting into profit here, but you know what I mean. Make some revenue. So we're not done. The question says, what should ticket prices be to maximize revenue? We don't know the ticket prices. We only know that 28,000 people have come. So we need to plug this into our demand function. So the demand function gives us our price as a function of attendance. So you plug everything in and you get 7. To maximize revenue, ticket prices should be set to $7. So pretty neat problem. It's sort of simplified, but it's fairly realistic, and it gives you an idea, how this is used in economics. All right, well, that's it for today. If you guys have any questions, let me know. Don't forget to check out the activity sheet. There are lots and lots of homework problems here that are really good. The video and Explore It are actually both really good for this. And of course, as always, the homework tutor will help you guys do some of your homework problems, at least the odd ones, right? So if you guys have any questions, let me know, and I will see you next video. Until then, bye-bye.